So I'm going to talk about Majorana Fermions and braiding and quantum computing and more general issues as well. But let me begin with a little history. Majorana, let me read this to you. This is from an introduction to an issue of Science recently, October 14, I think. Nearly 80 years ago, the Italian physicist Ettore Majorana proposed the existence of an unusual type of particle that is its own antiparticle, the so-called Majorana Fermion. The search for a free fermion, pre-Majorana fermion, has so far been unsuccessful. He, for example, suggested that perhaps neutrinos were Majorana fermions. But bound Majorana fermion-like collective excitations may exist in certain superconductors, and people have detected this, or so they say, and there have been a number of experiments about this. This is a very interesting elementary particle. It just interacts with itself to either produce itself or to produce nothing, energy. That's it. It's its own antiparticle. This is almost a mathematical entity. And in fact, we're going to see how it's related to fermions, regular fermions, and we're going to see how it's related to some more general issues. But you can try to imagine what this would be like. So the fusion algebra of a particle is the combinatorics of how it can interact. In this case, if you have many particles, then you would say, you look at the I particle and the J particle and see how they interact. They interact and produce some other particle or particles. That's the fusion algebra, the way they interact. In this case, the fusion algebra is very simple. P times P is equal to either P or star, P or 1. On the other hand, there's another kind of algebra that's normally associated with a particle, and that's the creation and annihilation operators for the particle. And I tell you, and then I'll explain to you why, the algebra for that's associated with a Majorana fermion is given by the simplest Clifford algebra. That is, it consists of this is for two Majorana fermions I've written here. A squared is equal to 1, but if you had another one, then B squared would be equal to 1, and they would anti-commute. All right? That's the creation annihilation or operator algebra for the fermion. So there are two algebras that are associated with it. Just so for an ordinary fermion, and I want to recall that for you, an ordinary fermion is associated with an operator which I'll call F, and a conjugate operator which I'll call F star. And one is regarded as the annihilation operator for that fermion, and the other is the creation operator. And those satisfy that their squares are 0, so we have no potency immediately here, and we'll come back to that later. And F star squared is 0, and then there's a commutator type relation, but it's an anti-commutator. FF star plus F star F is equal to 1. And this is posited by physicists because it's the exact analog of what happens with bosons and with the harmonic oscillator. If you started with a harmonic oscillator, but flipped for fermions, or just the anti-symmetry of the fermion, and the Pauli exclusion principle. So the first thing, FF equals 0, is essentially the Pauli exclusion principle. So that's the usual algebra for a fermion. Now, the relationship of that with somebody whose star is equal to itself is in the next bit of algebra here. So suppose that we had A and B, so that A squared and B squared are 1, and that AB plus BA is equal to 0. AB is minus BA. And suppose that I define U to be A plus IB and U star to be A minus IB. A and B are invariant under star. They just stay the same. But if we take A plus IB, and I is the usual square root of minus 1 here, and multiply U by itself, you see that we produce a little algebraic machinery that produces a nilpotent. You see? A plus IB multiplied by A minus IB is A squared minus B squared plus I times AB and also I times BA. AB plus BA is 0, and A squared minus B squared is 0 because they're both equal to the same thing. And so U times U is equal to 0, and U star times U star is equal to 0. So the basic picture of that nilpotent that is giving a fermion in the usual picture can be thought of. You can think of a fermion, of an electron, as a combination of two Majorana fermions that in mathematical. It has that pattern. And the other, the anti-commutation relation, I'm wondering whether there's a laser beam on this. There is. Little thing. The anti-commutation relation works just as well. See, you would have to do a little calculation, but let's do it as long as we're here. So I multiply these together, and you see it's the same as U plus U star times U plus U star. Why? Because the U squared is 0, and the U star squared is 0, so all I get are the cross terms, U star and U star U. But U plus U star is just 2A. So I get 4AA, and that's just 4, constant. So the other commutation relation works out as well. So this is the simplest instance of the relationship between Majorana fermion and fermion, and it's also a very interesting way to think about how a nilpotent operator arises, how those nilpotents that we've been talking about for the last 2 days arise. You can make a nilpotent like that, and it shows you that nilpotent algebra and Clifford algebra are tied right up with one another in exactly that way. So this is interesting mathematically, but it also is very suggestive that perhaps under certain circumstances an electron could be thought of as two other particles, and we'll come back to that. But what I wanted to emphasize here is that structure, which is physics. And now I'm going to take a digression that walks away from this for a while and then comes back. So the next part is motivated by T. Spencer Brown's notion of a logical particle that interacts with itself to either confirm itself or cancel itself. And this interaction combined with recursion leads both to matrix algebra and to the very elementary mathematics of the Majorana fermion. So I'm going to take a mathematical digression here, but the mathematical digression is one of great generality because what I'm thinking about is the nature of a distinction. And if I'm thinking about the nature of a distinction, then I'm thinking about what it is that can be observed either in our thinking or in our observing of the world at all times, every time, all the time. Whenever you're making any kind of observation, whether it's thinking of your own thought or examining what you see in front of you, you are always involved in a distinction. And when you're involved in a distinction, it means that there is present an observation and an awareness, and there is also present some kind of duality that says that is there and I am here, or this is there and the other is over here, and they are distinct from one another. Some distinction is being made that tells you that something is different from something else. But along with distinction come recursion. The fact that you can repeat, the fact that you can repeatedly identify something. It's part and parcel of having a distinction at all. So, for example, I look at the cup over there, and I look away, and then I look back at the cup, and there it's still there. And as I'm looking at it, it retains its cupness all the while. And if you think about what you're doing there, and I'm talking about the properties of ordinary, what physicists would call macroscopic observation, then you see that there is, if you try to describe it mathematically a little bit, you see that there is some kind of operator, which is the operation or operator of viewing it, and that operator gets an invariance. I get cup and then I get cup again. If I got cup and then I got squirrel and then something else, then I would be looking at a changing process. And of course, we're familiar with looking at changing processes. You can look into a waterfall, and then you find that you're at one level you see the whole waterfall as a whole, and at another level you're watching the individuation and process and changing, continually changing thing that's going on. So there are many examples of this, and there's a nice concept that's useful for that, which I call eigenform. And an eigenform is just a fixed point of some operator, all right? And you can make eigenforms. Let me go to the next slide and then come back. I can create an eigenform, for example, spatially. I can create an eigenform out of this nest of boxes, because I think of this nest of boxes as something which is invariant under putting one more box around it. If I put one more box around this, it has the same form, approximately the same form, since there are only finitely many boxes. But if I imagined an infinity of boxes, then it has exactly the same form. This is a kind of symmetry. Another kind of symmetry, of course, is that if I, say, take the operation of turning by 180 degrees, then this is somewhat invariant under turning by 180 degrees. And it's certainly invariant under turning by 360 degrees. So I'm looking at fixed points of operators and how they might be produced. In the case of the box example, it's a nice example because the operator itself, putting a box around it, actually can produce the eigenform for itself by composing itself with itself as many times as I like until it begins to become invariant. So one way to get a fixed point in general is to take some operation and then keep applying it to itself again and again and again until there is an invariance that comes about from it. So you can make forms out of nothing in that way. And then, I'll come back to this slide. Whoops, not that way. When you have the circularity of observation, like a universe observing itself in Wheeler's picture, or a form that is pointing into itself in this picture, or to give a more specific example, a linguistic form that fits into itself, like this one. I am the one who says I, and the operator in this case is O, the one who says, and I is what's invariant under O. Right? There are lots of linguistic forms of that kind. And if you start to think about it, then you realize that when we talk about the macroscopic world of observation, you could take on the notion that what you're talking about is the world of eigenforms. That you are examining things that are invariant under certain operations that you have available to you. So that's the notion of repeatedness in experiment, for example. And if the form that you're observing is the placement of a needle in a meter, it's exactly that, but in a very specific form. If what it is who's in the room or recognizing another person, it's harder to quantify. But we live in, that macroscopic world that we live in is the world of eigenforms. I also chose Wheeler's self-observing universe because it raises very nice epistemological questions, as you know, that he raised. He said, well, there's the Big Bang, and the universe evolves, and eventually becomes capable of observing the evidence from the Big Bang. And then he said, a phenomenon is not an actual phenomenon until it is an observed phenomenon. And so, in what sense is the universe actual before this observation or this collection of observations begins to take place? In what sense is the universe actual before it becomes eigenform? That was Wheeler's question, which I won't attempt to answer. But I have modified Wheeler's self-observing universe this way. And you might wonder, why have I done that, other than that it's amusing to look at? Because a knot is a very interesting kind of form. A knot acquires its form from its context. If this knotted tube were in nothing, it wouldn't be knotted. It's only knotted because it's embedded in two-dimensional space and self-relating in a certain way. Without that, it has nothing, it has no knottedness. The knottedness has to do with the context in which it lives. And whenever we talk about anything, we put it into some context. And again, there's a paradox for Wheeler's universe, because the universe is supposed to be everything. And so what is the context of the universe except itself? Let's go on. I think I already explained this slide, except for one thing. You can imagine building up an eigenform, like the infinite collection of boxes, by putting one box around another box around another box. But if you think of that, that's a process and it's going on in time, like this, box, another one, and so on. So there's a temporal process, or there's the spatial end of the temporal process. And when you think about this kind of thing, then you see this duality between space and time in a very concrete way, that you may imagine that the space is being built up through the process, or that the temporality is the unfolding of the spatial structure. And so it's good to have that around. We'll come back to it. Now, why do I say that I want to talk about Spencer Brown's calculus when I started talking about Majorana Fermions? Well, it's because of this striking thing here. Here's his calculus. I'm introducing it to you without explaining it. There's a mark, and this mark, oops, sorry. There it is. I got the right one? Yes. This mark has two ways of interacting with itself. If it's inside itself, then the two marks concentric to one another cancel and produce nothing. And that's a literal nothing in the plane. That star is is just an empty placeholder. I might write 2 marks equals blank, if you like. And 2 marks next to one another produce a single mark. The mark can relate to itself in 2 ways. It's either next to it or it's inside it. And when it's next to it, it confirms itself and just gives rise to itself. But when it's inside itself, it negates itself. And so if you start staring at this and wondering, well, what was this supposed to be? You realize, well, it's acting like the negation operator, right? Not is no knots at all. And indeed, that was the intent, that this would act like a negation. But this is also like a negation operator, but in a different mode, and we'll have to explain that. In any case, it was and is a way to redo logic at a slightly deeper level than the usual Boolean level, and it produces this logical particle, and the logical particle is exactly a combinatorial Majorana fermion. It interacts with itself to produce itself or produce nothing. So that's why I wanted to bring this into the discussion. But the epistemology of this is that the mark is seen to make a distinction. So the mark is meant to stand for the act of distinction. As such, you will do to it what you usually do to symbolism. You put it out there and make another distinction. And if you put it out there and made another distinction, then it's just a mark on the screen. But if it's your mark, if it's the mark you made, if you own it, if you're the producer of it, and you are the producer of it since you're looking at it, then it's also an extension of yourself, or it is yourself in some sense. And then it really does stand for the act of distinguishing. And then these are interpreted in various ways. One way of interpreting this is that, that things that fit together do each other in. Like if I really have something that fits something else, then basically everything disappears nicely. Or another way of thinking about it is that the mark is an instruction to cross a boundary. And then if you cross the boundary again, you can be back where you started. And on the other hand, the mark can be seen to name the space in which it is drawn. In which case, this is two namings of the space in which it is drawn, and two namings can be regarded as a single naming. Those are some of the interpretations of this in the logical mode or the linguistic mode. So as I say, in the formalism, the mark is seen to make a distinction. The formal language of the calculus of indications, the calculus of this, refers to the mark, is built from the mark. The language that uses the mark is inherently self-referential. The mark stands for a distinction, and it is a distinction from the point of view of the one who uses it. This calculus writes itself in terms of itself. And then I give you the very last lines of Spencer Brown's book, False Form. This is the last line of the book. We see now that the first distinction, the mark, and the observer are not only interchangeable, but in the form identical. And I don't mean that to be particularly mystical, as I said. I mean that to discuss the fact that when you have a distinction, you're involved in the distinction. And when you have an observation, you're involved in the observation. And that one should keep that in mind when thinking about physics, because it's very easy for us to make a mathematical model of observation, projection of some sort, and then decide that the observer has been removed from that and that it's all just somehow in the mathematics or in the formalism, but it truly isn't. And so this itself is a formalism that allows you to keep remembering that and perhaps compare what goes on in such a formalism with what goes on in more complicated ways of thinking about things. Now, I'm about to embark on a little more complicated thing now. I would like a model, a geometrical model, of how I could think about two entities that interact to produce themselves or to cancel. And here's a geometric picture that I like. So now I'm playing around a little bit. I have a surface here, up there. I have a little pair of pants surface, right? Upper boundary and lower boundary. Pair of pants are upside down. The two circles interact by coming near one another and going through a singular saddle point right here and turning into one circle. If you were to look at it temporally by slicing it, you would see two circles that come in and touch, and then they share a little bit, and then they untouch, as it were, canceling what they share and turning into one single circle. In the other picture, I have them concentric to one another, and one of them grows larger until it just touches the other one and cancels it out. And if you trace that with a surface in space, you would see this, these two tubes that are, one is inside the other like a kind of a vase, and a little bit of a curve at the bottom, where at the very bottom there's a little tangent curve, and that's where it disappeared. So you can think of abstract strings like this interacting and being Majorana Fermions, if you like. One picture. You see that is the same as the logical particles picture. You have two circles next to one another, which can combine to give you a single circle, and two circles concentric to one another, which can cancel each other out. And then I remind you also, we're playing around with the fusion algebra, right? I remind you that we could write P interacts with P to produce either nothing or P, and plus now means nothing. Plus means or. And that may remind you of a quadratic equation from long ago. X squared equals 1 plus x. And it has the same formal properties. So that if you let Majorana Fermions interact with one another more than once, you will pick up Fibonacci numbers. You see, p squared is star plus p, but p cubed is p times star plus p times p. But p times p is star plus p, which is 2p plus star. And if you then multiply by p one more time, you'll get 2 stars plus 3 p's. And then you'll get 3 stars plus 5, and 5 plus 3, 5 plus 8, and so on. 3 3 and 5 and 5 and 8, and so on. You get the Fibonacci numbers. So sometimes people call this particle a Fibonacci particle for that reason, that multiple interactions give rise to Fibonacci numbers of results. We'll come back to that too. And now I'm repeating myself. The circles interact either way, and it fits with the loss of form picture. But I'm interested in the epistemology of this, so I want to digress a little bit. If you were just doing logic, you would have the following question. Could you somehow make a Majorana particle, if you had the idea of making a Majorana particle, out of negation alone? We just did, but what happens if you're thinking in the usual mode? Well, Wittgenstein was thinking about this. He was thinking about the question, what is the relationship between his mirrored reality of the world in the Tractatus and the world? He forms a description of the world and talks about how the world is mirrored in his logical descriptions. And he says things like this. He says, that, however, the signs P and not P can say the same thing is important, for it shows that the sign negation corresponds to nothing in reality. And then later, how can all-embracing logic which mirrors the world use such special catches and manipulations? Only because all these are connected into an infinitely fine network to the great mirror. The limits of my language mean the limits of my world. The subject does not belong to the world, but is the limit of the world. And I think that it was things like this that eventually gave him enough problem so that he changed his way of working with language and epistemology in his later years. Because, as you see, he has this mirror, but it's quite distinct from the world, and negation isn't in the world. But in this other point of view, negation has fallen into the world as a distinction itself, and interacting with itself to reproduce negation, or to reproduce or. Because you can think of this as the negation of negation is nothing at all, and this is A or A is equal to A, but they live together. They live together this way. And we can have our languages and our descriptions contiguous with the world and not separated from the world. Just a side remark, how is it interpreted for logic? Like that. This is not A. A next to B is A or B. This is like what we were hearing in the last talk, where you remove the plus and you get 55. Here we are removing as much as we possibly can in the symbolism. And the mark is true, and unmarked state is false. That's the way you interpret it for logic. And I just thought I would also illustrate the formalism for you a little bit, since these would be interacting Majorana Fermions in some form. You see. That's allowed, right? Two can become one. But these two guys could cancel, and these two guys could cancel, and these cancel, and we ended up with nothing. Or in circles, these two guys cancel, 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 down to one. Or it could build up out of nothing, out of nothing, out of nothing. And now I want to shift to another part of the picture of fusion of Majorana Fermions. This is somebody's dream. It comes from a Scientific American article, and it's a specific dream. It's the dream that you might be able to have collectivities of electrons in the form of vortices in a two-dimensional situation like the quantum Hall effect. And that you would be able to manipulate the way in which these collectivities move around one another. Because when these collectivities move around one another, at least theoretically for that bit of physics, they get a phase change, which is not just plus or minus one. And consequently, you get a very nice trivial braiding. And it also illustrates the space and time relationship of braiding. I have here a braid, but you can see that this braid in the imagined picture is the result of, maybe it's the result of the puppeteer just holding those strands while the vortices, which are attached to the braids, of course not really, are causing the braids to wrap around one another, the braid strands to wrap around one another. And so over a period of time, these braid strands are getting braided by the fact that the vortices below them are moving around. Or it could be the other way around, that the puppeteer is somehow forcing the vortices to move or using his braid. Either way. It could be an observation or it could be an action. But the idea was, and still is, that perhaps we could control those quantum states in vortices in a flat, very cold plate. And it turns out that the vortices in some phases of the theory of this, at least, are Majorana Fermions. And it turns out that Majorana Fermions in that kind of context can have very non-trivial braiding. These are collectivities of electrons, and in the theory of this, they have very, very non-trivial braiding, and you might wonder how this looks, so I thought I would just give you a picture of that. Now this is a very condensed picture of this, and maybe I should draw something on the board to show you what's going on with part of it. If we have, well, maybe we don't.
Oh, I asked for them, but I guess...
Do we have any crayons? No crayons? Markers. You don't have to run off and get them. I'm fine without.
Oh, okay.
If they're not in the room, let's forget it. Okay, so we just look at my board. The problem with this slide is it has too many things on it, but I wanted to show you something interesting that it has, and that is right here. Just look at this. This little two-stranded object here, which is a piece of some mathematical formalism, and I'll tell you what goes on in a moment, it actually means two parallel lines minus a factor times two turnaround lines. But without drawing on the blackboard, I couldn't show you why I am so interested in things like that. But the idea is that then, when you put them together like this corresponds to this particle interacting with this particle to produce this particle. And the rule is that you have to connect the lines and have no free lines inside, all right? And then you see there are two basic ways in which you can do that, pitchfork little connections. You can do it this way, taking two down into this one and one going back around. Or you can have them both going back around. Or you can do something else. You could have a fourfold die, but I didn't allow a fourfold die in my situation. That would be another particle altogether. So we'll forbid that. It turns out you can forbid that by using the mathematics at a certain root of unity. And then these are the only two interactions that are possible. And you see these are exactly Majorana Fermion type interactions. These two interact to produce this, or these two interact to produce nothing. A little like the simpler one with the concentric circles, but in this case, little lines that are braiding, that are really meant to be braiding lines, but they get to turn around a bit like that. So those are the basic interactions in the model, and then it turns out that there is braiding in the mathematical model. That is, you can have a bunch of these things and strands coming down, and if you twisted some of these strands, those would get expanded into various combinations of sums of lines that either are going down or turn around, and you can calculate how the braiding works, and you end up with a mathematical model of these particles interacting and braiding one another, and you get phases that they interact with, like these, certain roots of unity, certain phases, and then there are some other technical aspects of the model that have to do with changing basis and when you let them interact. Because, well, that part I won't bother you with. I just wanted to show you the sort of surface structure of what the so-called Fibonacci model looks like, which can produce unitary transformations that come from braiding of Majorana Fermions, like the collectivities of the electrons. So there's a simple mathematical, simple for topologists mathematical model of how to do this braiding and get unitary transformations. And then I need to say something else to you about what the background of that is for just a second. I'm talking about quantum computing here. I'm talking about making the phase changes that those collectivities undergo, reining it in so that it could be used to compute something. So that's a simple quantum idea from quantum theory that people have been studying for a long time. But it's a very simple idea. The idea is, well, a quantum process is a unitary transformation. Maybe you can use finite dimensional ones, and that would make things easier. But if you can imagine some mathematical problem that you would like to solve, if you can translate that problem into a unitary transformation whose statistics, when you observe it, will give you the answers to your mathematical problem, then that's a quantum computer. Because what you can do is you can imagine realizing the unitary transformation, making it actually happen in the world, and then you have this black box, which does the unitary transformation, and you keep observing the end result of the black box over and over and over again and getting the statistics. And if you designed that unitary transformation in such a way that it was actually computing the math problem you had in mind out of the statistics that you would see, then you would get the answer after a while. And it turns out you can do that, and you can, for example, factor numbers in principle faster than classical computers, according to Peter Shor, by using his algorithm, which is, in fact, a design of a certain unitary transformation whose statistics you observe. So all you have to do is build a computer to do that. You have to build the actual physical apparatus that does this quantum process. And of course, that's not easy because of decoherence. And so no one has really quite yet accomplished this aim except in the lab for a very small number of quantum bits. And certainly not managed to factor large numbers yet by using Shor's algorithm. But then there have been many different schemes for hopefully doing that. And one of the schemes that people are interested in, for example, the Microsoft people are interested in, is using the quantum Hall effect and the collectivities of its electrons and the kind of thing that I'm describing here to control that and use that to produce the unitary transformations that would be at the base of a quantum computer. And there are other schemes, of course, as well. And while it may still be a long time before people make real quantum computers, the mathematics of this is very interesting. And the reason I'm bringing it into the theme here is because you see that you start with this very elementary idea of a Majorana fermion, which is so close to the notion of just bare distinction that it's worth thinking about epistemologically. And it does have its possible realizations. And those realizations are very closely related to topological things. Here, the description of how it's related to braiding is a little complicated, and I kind of eliminated it from the discussion, except to give you a little bit of a hint about it in this slide. But we're going to see braiding on the other side as well in a few minutes. Just checking the time. Okay. In a few minutes, we'll see that braiding is also related to the creation and annihilation algebra for fermions. So braiding occurs on both sides. That's another reason I'm very fascinated by this, that braiding is very close to the notion of a fermion, however you take it, whether you take it in terms of the way they interact, or if you take it in terms of creation and annihilation. You're going to see topology there either way, but I'm just running ahead of myself with that. So as I say, this Fibonacci model, the one I just indicated to you, yields a braid group representation that is universal for quantum computation. That is, the braid group representation, the phase relations that are coming out of that, are strong enough so that you can build any unitary transformation you want, finite dimensional. up to approximation. So it's as though underlying all of quantum mechanics in some sense up to density is topology grading, that you can at least say that mathematically. Of course, it would be an entirely different thing if I could show you how, by looking at the universe in an appropriately fundamental way, we would see that all the processes of the universe are coming out of grading. I don't have to do that, but it would be fun if I could, right? Maybe that's possible. But this is a mathematician's construction, that you can make these grade group representations dense. Well, there's our dream again. Now I'm going back. I want to show you something else. I want to show you how algebra, matrix algebra, the square root of -1, really all of matrix algebra, in particular the little Clifford algebra we started with, all of that emerges very naturally out of the recursion or the eigenform in its most rarefied aspect. So here's the eigenform again, just iterating a transformation on itself. But I want to turn it into something a little more numerical to look at. So I'm going to let it be plus and minus 1. And I'm going to replace the cross here by minus 1 over x with malice aforethought, all right? Because now I have a favorite mathematical eigenform in front of me. If I take the transformation, t of x is minus 1 over x, then I is the solution to that, right? Minus 1 over I is I. I squared is minus 1. Right? Okay. So I is a nice eigenform. On the other hand, if you think of it temporally, if you keep applying it to itself, well then you could have started with 1, let's say. The transformation is t of x is minus 1 over x. You could have started with 1. And then minus 1 over 1 is minus 1. And minus 1 over that is plus 1. And minus 1 over that is minus 1. And so I get an oscillation. The oscillation never arrives at the square root of minus 1. It's just always oscillating back and forth. The square root of minus 1 is a leap that you took to a solution to the eigenform. And it is like I am the one who says I, in that if you tried to iterate to produce the I, you won't get there. Lots of eigenforms have the property that they are simply the solutions to the equation, but you don't get there by approximating, or at least no one knows how to get there by approximating. The well-known question of is it possible to produce an intelligence or a consciousness by somehow iterating the process of producing machinery is similar to trying to produce I by applying the one who says to the one who says to the one who says, and if we apply it infinitely often, we get a solution to the one who says I is equal to I. But did it actually produce what you wanted? Somehow similarly with I, one leaps to the solution, and that's what people did long ago. They said, well, we'll just assume that there is somebody there whose square is equal to minus 1. And on the other hand, when you, in this case, when we have the oscillation, you could ask whether somehow out of the oscillation itself, could we get the I, but we'll have to be more intelligent than just saying that the oscillation itself is the I. We'll have to figure out how to multiply. Can we do that? Well, there are two ways to look at this oscillation. One way is that it starts at minus and goes plus, and the other is that it starts at plus and goes minus. So that's a suggestion. Maybe that's I and its conjugate. Well, I'm going to, I see I did this too quickly on this slide because I went from plus and minus to A and B. But if you could bear with me, because I don't have a blackboard to make it more palatable, I'm thinking of the A and the B as the plus and the minus. And I'm introducing an operator which shifts between one and the other, the AB and the BA, by multiplying on one side or the other by it. So if you meet this operator and you put it on the other side, it's as though you temporarily shifted the sequence. The sequence is going plus minus, plus minus, plus minus. And if you push the operator eta across it, it shifts it to the other phase of it. It's as though it shifted it in time up by one step. So I'm introducing a temporal shift operator, which I'm calling eta, all right? And then I'm going to do two things. You'll see what happens in a moment at the bottom of the slide. I'm going to think of combining waveforms like this, discrete waveforms or discrete processes, term by term. So if I had underneath this a CD, 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 then they would combine by just taking A and C and B and C and A and C and B and D and A and C and B and D, like that, term by term. On the other hand, I'm going to define I by the equation 1 minus 1 eta. And now watch what happens. You take 1 minus 1 eta, this is temporally sensitive now. If somebody else meets it, it can get time shifted by the eta. The eta is a little bit of temporal process placed in the algebra. You put them together and watch what happens. You multiply 1 minus 1 times eta by 1 minus 1 times eta. And eta shifts across a 1 minus 1 to meet itself. And the 1 minus 1 turns into a minus 1, 1. Because it got shifted. And they combine to give you minus 1, minus 1. And the etas, well, I'm assuming that if you do eta twice, you're back where you started, because that's what happens. If you shift 1 minus 1 and then shift it again, you're back to where you were. So eta squared is equal to 1. And we have constructed a model of I out of the oscillation, out of the attempt to just iterate the process. But we've done it by imaging time into algebra in this way. Eta is temporal, and this is a temporally sensitive entity. If something comes up to it, it can get shifted by the eta, and shifted if you think of it as a process in time. So that what happened was that you had these two temporal processes, the 1 minus 1 process and the minus 1, 1 process. And they're fitting like this. But one of them has an eta in between, and because of the etas, they get shifted by 1 notch. And then the minus 1s are just meeting one another with the plus 1s, instead of the plus 1s meeting plus 1s and the minus 1s meeting minus 1s. They go out of phase with one another, and you get that I squared equals minus 1. So I squared equals minus 1 if you make a model of this kind. And so what have we constructed? We've constructed that first Clifford algebra. You see, here is E, and E itself is not temporally sensitive, and when you square it, it just multiplies its constituent parts and gives you a 1. E eta, on the other hand, that's the I, and there's a mistake on my slide. That's a nice mistake. The eta was supposed to shift over to the other side, and it didn't in this slide. Altogether wrong, this slide. Too bad. The eta was supposed to be on the other side. That's all, right? E eta is minus eta E. Sorry about that. It's correctly written there. So there's our Clifford algebra. E squared equals 1, eta squared equals 1, E eta equals minus eta E. And in the Clifford algebra, if you take the product of these two guys who squares 1, you get somebody who squares minus 1. So what you see is that in this first arising of the square root of minus 1, it's happening in a non-commutative situation. The square root of minus 1 really fundamentally is part of a non-commutative situation. It's only by dint of our education and the history of the thing that we thought that it was a commutative situation, and then there were later developments of non-commutative situations. The square root of minus 1 was always part of this commutative situation like this, from this point of view. Okay. And if we think of those as temporal and spatial elements, then you can think of the fermion that you would create out of them as combining the spatial nature of this and the temporal nature of this into one fermion. But that's all just mathematical talk about making the combinations. it is true that these are fermion operators now, and we have arrived at the Majorana Clifford algebra in a perfectly natural way by thinking of discrete process. And I think maybe this is where we should take a break, or do we go to 12 and take the break?
Well, we were originally down to go to 12, but if you
All right,
could
well, I'll do 7 more minutes and then
Yeah.
take the break. So at this point, you see that it's not just the square root of -1 that has emerged from the structure of the oscillation, but the non-commutative algebra of the split quaternions. That's another term for E eta and the algebra they generate. I'm going to use this as an excuse to follow this over to the Dirac equation, and we'll do more. But we've also uncovered a source of matrix algebra, and it's worth seeing what I mean by that by re-looking at the formalism again. I can form in this arena that I've constructed for you of waveforms and waveforms with little temporal shift operators on them. I can form sums of them. So I can form sums of AB and things of the form C D eta. I say that, in fact, this corresponds to a 2 by 2 matrix, just like that. That's exactly what it corresponds to. And the algebra is exactly the same as the algebra of 2 by 2 matrices. Now let me check to see whether I had a better slide for that. No, so I'll have to ask you to visualize something. If you believe that top part of that slide, then you should imagine what happens if A and B are 0 and C and D are 1, which means 1, which just means eta, eta itself. Where is eta itself? It's A and B are 0 and C and D are 1. The matrix, the familiar matrix, 0, 1, 1, 0, right? That matrix. That matrix is a permutation. It permutes 2 things, right? It squares 1. So that's exactly what eta did. And then if you think about what I've called AB, you see that I'm calling AB the standard diagonal matrix. And what about the square root of -1? Well, the square root of -1 is when C is 1 and D is -1 and A and B are 0. And that would be a 0 here and a 0 here and a 1 here and a -1 there. Right? Anti-diagonal matrix with a 1 and a -1. Well, you're also familiar with that. That's one of the ways to represent the square root of -1 in matrices, right? And now you're looking at it in a different way, though. You didn't think before, unless you were thinking about this interpretation, that the 1 and the -1 in the anti-diagonal of the 2 by 2 matrix that represents the square root of -1 is the plus-minus process that lies behind the square root of -1. It's actually there. So one way to think about this is we reinvented matrix algebra. And indeed, in fact, we can reinvent arbitrary n by n matrix algebra in a similar way. And I'd be happy to talk about that, but not right now. So that means that 2 by 2 matrix algebra, which is all we're looking at here, can be thought of as a kind of species of hypercomplex numbers where you have an eta squared is equal to 1, and eta applied to anybody is the same as eta on the other side applied to its flip, where you flip the coordinates. That's a nice hypercomplex number system, very non-commutative, and full of structure. Just that. You can do a lot with it. So that's the interpretation for matrix algebra. Here's an example that you might want to think about. We can represent a point in space-time as a 2 by 2 matrix, plus x, t minus x, y plus iz, where I is already in there as a commuting I, and y minus iz. You can think of this in terms of what I just said, and then the spatial part is the part that corresponds to the first part of my decomposition is the t plus x, t minus x, where these two have been displayed together, and the I is over here on the other side. So you could think of this as having to do with a process, and the other one as having to do with imaginary values on either side of the process. There are lots of metaphors that are associated with representing a point in space-time this way. And in this, you'll notice that we have the Pauli matrices, and many other simple matrix systems are coming out naturally here. I like to think of the metaphors in terms of this kind of a mandala, where you have process and form instantiated together in that way. So to summarize, we can regard E and eta as a fundamental pair of Majorana Fermion operators. It's a formal correspondence, but it's striking how the Majorana Fermion algebra emerges from an analysis of the recursive nature of re-entering distinction, and the fusion algebra for the Majorana Fermion emerges from the distinctive properties of distinction itself. We've seen how the Clifford algebra emerges, and that the mark embodies the fusion algebra of the Majorana Fermion. I do think at this point this is a good place to stop, and then we'll continue after a little break.
Okay.
Yeah.
Should we take 10 minutes?
I was curious about the word distinction that you used. Do you know about Bentley and Bentley's book called The Knowing and the Known?
No, I don't know.
Okay. Bentley and who is the educator? Forgot his. Dewey and Bentley in 1949 wrote The Knowing and the Known, and they have about 60 over 100 distinctions in self-knowing.
That they think are quite fundamental, huh?
Well, they're developing a theory of knowledge.
Yes.
But some of the initial remarks that you made reminded me of their work.
That would be inevitable.
They use distinction because they don't want to use the word duality. And they insist they don't use duality.
Yeah, and I think I do the same, because I don't want a distinction to be only a duality. It can be a joining just as well as a separating.
That's part of their definition. Now, the history of that includes Arthur Lovejoy at Johns Hopkins University, who wrote in 1930 the case against dualism. There was a book. Okay, I'll talk to you about that later. It's a long history.
Well, we're in the break.
Okay,
so people can get off.
Okay,
keep talking.
So what Lovejoy pointed out is that Dewey and Bentley were Americans. They were influenced by a German philosophy, and who rejected concepts of duality and dualism. So he wrote why Dewey and Bentley in particular were against dualism, and then they came out with this book in 1949, about 20 years later, on their theory of distinctions, not dualisms. But they are two distinct things. But your theory seems to fit the initial part of it on self-reflection, their definitions.
It'll be interesting to see what they collect. If you start collecting, you say, well, I'll think about fundamental distinctions, whatever is fundamental for me, and then you start writing them out, and you say, oh yeah, right. Some of the things I do are really fundamentally related to this distinction or to that one, and it depends on who you are and what you do, what you will end up with. And you'll end up with a list of about 200, easily.